Hello and welcome to day 9 of the advent of compiler optimizations. Today we're going to look at some more loop optimizations. Let's dive straight in. Over here I've got a routine that's going to output the times table. So we're given the value, the number, the table number. So this is like your nth times table. How many values we're going to output, and then a very unsafe spot to write to, which is output. And we're not going to check any bounds or anything like that. We're just assuming that the output is at least count integers long. So we're going to loop from 0 through to count, and then we're going to say star output plus plus is equal to index times table. And we're going to expect to see a multiply in the loop because we're multiplying each time by the table. But that's not what we're seeing. The compiler, once again, is clever. Let's have a look on the right-hand side. We can see we are saying, are there 0 elements, in which case we can skip immediately and return. Then we're going to move sign extending. So that takes ESI, which is a signed 32-bit integer, and we're moving it into the RSI 64-bit register. We're setting our loop counter index to 0, and then we are multiplying RCX, and then we are, what are we doing? Well, you get a sort of window into me being confused reading the assembly code here. We're taking RSI times 4, which is to say the number of elements that we're going to be producing, and multiplying it by 4. And then we've got RDX, which is the base of the output table. So what this is doing is getting the address of the last, or the one past the last of the output. So this is using LEA to do an add and a shift, but it's also kind of the actual use for an LEA instruction. We're getting the effective address of the element one past the end of the array. So RCX is going to be the stop point. Now we see the thing the compiler likes to do, which is to get ahead of itself in the loop. It is adding 4 to the output parameter already, and then it's writing to the location -4, so it's just undoing the add it just did, and it's putting that writing the EAX value, which is our current output value, to that spot in the table, and then it is just adding table to that value. So it has rewritten the code to be something like the equivalent of int current equals 0, and then it says star output, I can't type, star output plus plus equals current plus equals table. Now in theory this should generate the exact same code, and it does. So the compiler has rewritten my loop where I'm multiplying by an incrementing value by something where we've made an intermediate value and we're just adding to it. This is a great optimization. It's removed the multiply from our loop and replaced it with a simple add at the expense of just one extra intermediate value. These are called induction variables. The compiler's really good at pulling them out, which is great. And in fact, on our earlier days, we were already taking advantage of that. When, for example, we looked at the sum over a vector, the compiler had replaced our indexes with a pointer that it was walking forward, and that's another sort of variation of this theme. Now, interestingly, when I was preparing this, I thought it might be able to do some other optimizations. So for example, if we wanted to output a sequence of squared numbers, so let's just write this instead. So let's call this output squares. Output squares. Let's just have an output. And then I'm just going to say, let's take a int num squares to do. And for int x, x equals 0, x is less than num, plus x, star output plus plus equals x times x. So here we're also incrementing x each time, but we're squaring it. And I was expecting it to use an identity which sort of derives from maths. If you think about it, each square number is 2x greater than the previous one. So 1 squared is 1, 2 squared is 4, which is the gap between those is 3, 3 squared is 9, the gap between that is 5, so you add 1 and then 3 and then 5 and then 7 and 9 and so on. So the compiler should be able to intuit that, but it doesn't. And it uses a multiply instead, the imul edx, EAX to actually do the square, and that's fine. It's a relatively fast operation these days. While writing the blog post that accompanies this video, I theorized that perhaps the reason that the compiler chose imol here is that it knows that they can overlap during multiple iterations of the loop, because there's no dependency between each loop iteration other than the loop counter, which is being incremented pretty quickly, and that's a fast operation. That probably is not the case anymore now I thought about it as I'm filming this, but I'd like to show you some cool tricks that Compiler Explorer can pull anyway. So what I would like to do is show you a visualization of the overlap of each loop iteration. This is kind of advanced, so that if you're already kind of like, oh, that's cool, then maybe you could skip till tomorrow, but let's dig into this one very quickly. So I'm going to take the code of the body of the loop, and I'm going to switch to analysis mode over here. Analysis. This lets me paste in just a snippet of assembly code, and I'm going to pick the LLVM machine code analyzer. And the machine code analyzer will simulate a processor, and it will give me some kind of feedback as to how fast it thinks this loop is. So the thing we're pasting in is the body of a loop, and already it's telling me that it's simulated 100 iterations of this loop, which would be 600 instructions. There are 6 instructions, that's times 6, that makes sense. It would take, in theory, 156 cycles. This now assumes no cache misses and no branch mispredictions. It just gives you the kind of the best case scenario for the instructions that are in this loop. And it says that this 6 instructions generate 6 micro operations. And that's a kind of deep topic, but the thing I like to do is to turn on the timeline view, and then I'm going to maximize this window and scroll down to the bottom, past all of this nonsense, and what we get here is a relatively simple ASCII art simulation of what's going on inside the CPU, at least according to LLVM MCA's understanding of what the Intel CPU is doing. The way to read this is that time is going from left to right. Each step right is one more cycle, one more machine cycle. So if we look at the first column here from the 0 and down, we can see that the first 4 instructions here, the mov, the imol, and another mov, and the increment, have all been put into state D, which is decode. So capital D is decoded, lowercase e is beginning execution or midway through execution. Capital E is the last cycle of execution, where the results of that execution are now available to other instructions that might be depending on it. And then the capital R is retirement, when that instruction has fully completed. And retirement always happens in order, although the other parts might happen out of order if the CPU can show that they don't interfere with each other. So here you can see we moved EAX into EDX, and then the multiply happened as soon as the move had completed. So the multiply was waiting for it. Here, this capital E of the last cycle of the mov corresponds to the first E of the imol, and the equals says that it was blocked. On this next mov, which is storing the result of the squared value, you can see again that had to wait for the multiply to complete, and so there are lots of stalls here. But the increment of the loop counter, inc_rax here, had already completed by that point. It took 2 cycles to finish executing, and the comparison happened immediately after that, and as well as the jump. So we've got a compare and a jump that happened, and they've been predicted correctly according to the simulator here. And then the next loop iteration is already going on. So you can see that down here in line 63, we're already doing the next multiply while the first one is still completing. So there isn't really too much disadvantage to the multiply being put into the loop, because the latency of it is hidden by the fact that the CPU is executing lots of things at once. So we get to see a little example here of how clever modern CPUs are. We've seen that the compiler can be pretty darn smart inside loops by replacing multiplies with adds and taking advantage of the out-of-order superscalar CPUs that we have these days. Tomorrow, we'll look at some other loop optimizations, specifically unrolling. Hope to see you then.